All right, welcome to The Explainer. Today, we're diving into a story about a true unsung hero of the power grid. We're talking controlled explosions, mind-boggling temperatures, and the incredible device that, honestly, kept our lights on for decades.
So let's just jump right in. I want you to picture this. Lightning strikes a power line. A massive, unstoppable surge of electricity, a fault, is tearing through the grid. You have, what, milliseconds to stop an electrical arc so violent it can melt steel and trigger a citywide blackout? So how on earth do you fight a fire like that?
Well, this is the story of the device that was built for exactly that job. Think of it like a heavyweight electromechanical bouncer for the power grid. It's just standing guard, ready to face down that raw, untamed power at a moment's notice.
To fight that electrical inferno, engineers needed a switch. But, not like a light switch. They needed a super-fast, incredibly powerful guardian for the entire system. And that's what a circuit breaker is. Its one and only job is to safely cut off that massive, dangerous flow of current. Period.
Okay, but here's where things get really interesting. You have to hear the solution these early engineers came up with. To stop a violent, super hot electrical arc, they decided to use oil. Yeah, flammable mineral oil. I know, it sounds completely backwards, right? Like fighting fire with gasoline. But trust me, it was absolutely brilliant.
And that's how we got the oil circuit breaker, or OCB for short. This device uses a whole bath of mineral oil, not just to, insulate things. Nope, that oil is its main weapon. It's what it uses to physically extinguish that electrical arc during a huge fault.
All right, so let's get into the nitty-gritty of how this actually works, because it's basically a very, very precise, controlled explosion. So first step, a fault happens. Inside the breaker, two big metal contacts start to pull apart. But the electricity is just so powerful, it doesn't care. It just jumps across that gap, creating this incredibly violent arc. And this is where the magic really starts to happen. And to give you an idea of the sheer power we're dealing with here, that arc is ridiculously hot. We're talking up to 5,000 Kelvin. To put that in perspective, that is literally hotter than the surface of many stars. Just insane. So that crazy intense heat, it instantly vaporizes the oil right around the arc. It basically boils it and breaks it down into a huge bubble of mostly hydrogen gas. And this bubble expands, get this, to about 1,000 times the original volume of the oil. That creates this massive high-pressure blast inside the breaker. And that blast does two really important things. It cools the arc down, and it de-ionizes it, which is just a fancy way of saying it robs the arc of its ability to conduct electricity. And just like that, the arc is snuffed out for good.
I mean, this basic idea was just so effective that engineers spent the next several decades just refining it. So let's take a look at how these things evolved from, simple, clunky brutes into much more sophisticated machines.
So the first designs were what we call bulk oil circuit breakers, and they were exactly what they sound like. Just imagine a giant steel tank, like a big bathtub, filled to the brim with oil, with the whole breaker mechanism just dunked right inside. They were simple, they were tough, and they were cheap to build. The problem, they were incredibly heavy, and well, having a giant tank of flammable oil sitting in your substation is a bit of a fire risk. So that challenge led engineers to develop minimum oil designs. And this was a much smarter approach. They used just enough oil in a very targeted way just to put out the arc. This made them way safer, a lot lighter, and much more efficient. And of course, the innovation didn't stop there. Engineers got even cleverer. They developed these special chambers. They're sometimes called explosion pots, which is a great name, and their whole job was to contain and aim that hydrogen blast right where it needed to go. They even came up with designs that use pistons to physically shoot a jet of fresh, cool oil directly into the arc. Just an amazing way to make the whole process faster and even more reliable.
Okay, so you've designed this thing that handles a literal electrical explosion inside itself. The big question is, how do you prove it's safe? How do you prove it's going to work? Not just once, but every single time, for years and years out in the field.
Well, the answer is something called type tests, and they are absolutely grueling. They take a sample breaker into a special high-power lab and they basically torture it. They hit it with artificial lightning, they run it so hot for hours on end it's almost glowing. They force it to break currents way bigger than it should ever see in the real world, and they open and close it thousands and thousands of times to make sure nothing breaks. Only after it survives all of that, this real trial by fire, does the design get certified. And it's because of that super robust design and all that insane testing that these oil circuit breakers became the absolute backbone of our electrical grid. I mean, for the better part of a century, these were the dependable workhorses out there, 24/7, just keeping the power flowing.
And you really could find them everywhere, from the biggest power plant substations protecting the entire grid, all the way down to older industrial factories where they just stood guard over huge motors and transformers. For decades, if you needed high-voltage protection, the OCB was pretty much the default choice.
Which of course leads to the obvious question, right? If these things were so good, so effective, so reliable, why are we replacing them? Why are they disappearing from substations all over the world? Well, the answer really boils down to two things: risk and maintenance. First, you just can't get around the fact that a huge tank of flammable oil is a fire hazard. It just is. And second, these things require a ton of upkeep. You have to constantly test the oil to make sure it's not contaminated and to check its dielectric strength, which is just a measure of how well it's insulating. And this is really where modern technology just leapfrogged the old OCB. Newer breakers use things like SF6 gas, which is non-flammable and an amazing insulator, where they put the contacts in a total vacuum, where an arc literally can't even form. Both of those options are way safer, smaller, and need a whole lot less maintenance.
So that kind of leaves us with a final thought here. This simple, really powerful idea, using a vaporizing liquid to kill an electrical arc, it served us incredibly well for generations. It makes you wonder, right? As our power grid gets more and more complex, what other foundational, maybe even old-fashioned ideas are just sitting there, waiting for someone to rediscover them and reimagine them for our future?